So welcome to San Diego, Kubernauts. I've not been back to San Diego since I was actually born. I was born in the area, but have never been back. So this talk is living with the pathology of the cloud and how AWS runs lots and lots of clusters. I couldn't fit in lots and lots. I think there's like a 75 character limit, so I had to abbreviate it. We'll jump right in. So first, I kind of want to give a little bit of background on Amazon EKS. It's our elastic Kubernetes service. You may have heard of it. This talk, before I jump into even EKS and sort of what we do and what it is not really intended to give you, you don't have to follow all of what we do to build a planet-sized, planet-scale application. But I kind of want to pull back the curtain a little bit, and so you can kind of see how does AWS run a service or build a service, and kind of talk about some design decisions, trade-offs, nuances. So there's not always a best answer to everything. So what are some of the decisions we made for operating our service? So before I even jump into the service itself, the kind of first thing I want to set, first just some level setting, is what are the EKS service priorities? So at Amazon, you may have heard this if you've heard other Amazon talks talking about services. The first real two things that we really value in operating our services are security and operational reliability. These aren't just things we say. We actually like say these to each other a lot, day to day. When we get like a security issue, whether it's a CVE or just something that we noticed or something that's even a concern of a customer, we take that like very seriously. That gets escalated very, very quickly, and we drop everything to make that right. And that goes the same for our operational reliability as well. Like our customers trust us to run I'm assuming you here are some of our customers, to run your critical applications on our service. And so we take that really seriously, and we want to offer a really highly secure and stable environment for you to do that. So to date, like EKS has created literally millions of Kubernetes clusters and run hundreds of thousands of cluster upgrades. So this is something that like we do a lot. So we've developed a lot of experience doing, but we've also like highly automated as well. So we want you to be able to benefit from our operational stability. So in the last, I guess, year and a half since we launched, we've seen like a number of Kubernetes CVEs come up, and so over that period, for even some of the more recent ones, you might not have even known that we necessarily upgraded your cluster before the CVE was even announced. That's kind of the level that we operate, and we take like security and operational stability very, very seriously. We want you to basically rely on us to make sure that the the control plane works, and your applications run. So backing up, here's kind of just a high-level overview of what does the sort of service map look like for when you have an EKS cluster. So what does AWS provide for you? Today it's really, well, up until yesterday, it really was just the managed Kubernetes control plane. So what does that mean? Well, if you're running Kubernetes, there's the sort of three primary components: the Kube API server, the controller manager, the scheduler, and then there's the etcd database behind it. etcd is the key value store database that's open source. We'll get into a little bit more of etcd later. But we run that across multiple availability zones for you for high availability. We automatically fail away from any specific zone issue if there's an issue affecting a specific zone. We maintain that we actually implement this with auto-scale groups, just like you would as a customer for your own applications. Using a lot of the same AWS primitives we'll get into a little bit. We have a network load balancer, and again, another AWS product, surprise, in front of the API servers. And then you, the customer, have the data plane, what we're calling, in your account. So that's where you see your EC2 instances, and those can be EC2 instances you launched in the console. It could be more likely probably auto-scaling groups that you manage with either CloudFormation or Terraform or something like that. or COPS, or any, or not, I guess not COPS in this case, but COPS does this sort of similar thing for its data plane. So a feature we just launched yesterday is manage node groups, and you see that here. That feature, I won't go into a huge feature pitch, but the basic premise is that you can click a button and get nodes and get managed upgrades. So you can look for more information there. But back to kind of our service, well, how do we build this? Well, as I've been saying, it's all based on all these AWS primitives. We're not using any super secret virtualization technology that is not available to our customers. EKS is actually implemented with almost entirely, actually I could say entirely public AWS services that you can use. There's a few APIs, like things like billing that, why would we expose that as an API? You don't need that. But for the rest of the service, it's all public APIs. One of the other things that we do is, as we've built this service, is we've adopted what's called a cellular-based architecture. This is becoming more and more popular inside AWS, and we're starting to talk about this more. What this means is we have sort of independent silos of operation. And I'll kind of show you what that looks like in a second. These can be, depending on how you implement it, logical or physical. The silos can, by physical, I mean, it could be, say, a zone, or it could be a logical across zones. What this really helps with is horizontal sharding. And when do you choose sharding? You choose sharding when you have a large scale. And that's what AWS is sort of known for, right? Like we operate at really large scale. We have small, high-functioning service teams, and they can't do one-off things for every customer that we operate. So we really need high performance, high scale operation here. So this horizontal sharding sort of helps us scale out, not up. Especially when you do operate at scale, you typically do hit limits. And I don't just mean AWS limits; these can be physical limits, right? Like how many packets can you get in a network connection, or how much bandwidth, or how much CPU you can get on a box. Like, there are a number of limits that you start to hit. So that's why we favor more of the scaling out model. Other benefits to this cellular architecture are you get reduced blast radius. If one cell is affected by, say, a downstream service or a misconfiguration or something like that, you don't end up affecting everything in that, we'll call it partition, or that group of cells. We actually, we shard these cells by region. So EKS is a regional service, so you use EKS in US East 1 or US West 2 or in Dublin or some other AWS region. But we have, in some of our bigger regions, up to 20 cells, or more than 20 cells. So the idea being, when we start a rollout there, if we start noticing issues in one cell, we block the rollout, roll back, and then only customers in that one cell are affected and not the rest. And then some of the trade-offs to this are, again, not everything is peachy, right? There's work for this. There's increased complexity. If I have, say, a customer cluster, we'll call it a customer cluster ID, like a unique identifier for a cluster, and I'm an operator and I need to debug an issue, I can't just look up from a single database, oh, which cluster is this? I have to do a little bit more indirection because we're split into separate shards. This also necessitates the upfront investment in operational tooling and automation. Because when you have n copies of something instead of just one, if you've ever, for those of you who are AWS customers, which I imagine a large portion of you are here, if you have just one Amazon account, like, no shade, that's fine. But what we highly recommend is splitting up if you have a pre-production environment, put that in a different account. Because that helps, for some of these same sorts of reasons, insulate you. So this, if you've worked across multiple Amazon accounts, you sort of have started to see the need for, okay, I need tooling because I can't just query it in one account. Imagine that times 20 per region. So you have how many public regions are there? 18 now, I think. And you have numerous cells. You're talking about hundreds of cells. So investigating a specific issue requires, again, upfront investment in in this automation and tooling. So how is a cluster created? You as a customer say, okay, you have your command line, the AWS CLI, you say AWS EKS create cluster, or maybe you use EKS Kittle, or you use the console, or whatever it is. Well, you, in the end, are the customer making an API request against an API. And in our case, that's Amazon API Gateway. We actually implement our service with Lambda. So we have a Lambda-backed, API Gateway backed by a Lambda function, which will take your request, do some lookups about your account, about your authorization, authentication, all that. And then, can we create this cluster? Okay, let's create this cluster. And this gets handed off to, through a number of steps, but it goes to a step function. So we're using, again, same sort of public AWS tooling that you're, and products that you're familiar with. And in this whole cellular-based architecture, even if you have all these cells, you still have to have a singular front end, right? Like, there's a single ingress point for all this. So we try to keep that front end layer as thin as possible and sort of shard out to these various horizontal cells. So when this step function gets your cluster, create request, the next thing that it does is obviously process this request and creates a CloudFormation stack for your cluster. So in this setup, we create a unique stack for your cluster, which contains all the other AWS components required for that specific cluster. And we sort of think about, and just on our team, when we talk about our control plane team and our data plane team, our control plane is all the Lambda, API Gateway, DynamoDB, all that fun stuff. And our data plane is the actual sort of EC2 instances and components that you, the customer, interact with when you interact with Kubernetes. So when you create the AWS EKS cluster, you're using the AWS CLI. When you start interacting with the cluster, you're using the Kubernetes kubectl. And that is talking to a different endpoint, right? It's not the AWS EKS service. It's a different endpoint backed by, again, the API servers. So this cluster, how is it created? So like we said, there's a step function, it creates this CloudFormation. But what else all in that CloudFormation? Well, there's a number of things. So it's a progression, and this is sort of why you see a common question we get is like, why does the EKS cluster take so long to create? So today we've just it's something that we are continually optimizing and will be optimizing more, but we create you a specific VPC for your cluster. So each cluster gets its own AWS VPC. We create 2 autoscale groups, one for etcd, one for API servers, then IAM roles for those, and elastic load balancers in front, as well as a number of other resources, like KMS keys, all those kinds of things. So that's sort of the high-level stack of when your cluster is created. These are all the things that are going on in the background. So yeah, again, this is just kind of the high-level view. So now that the cluster is created, let's talk about some of the more fun stuff, the failure stories. So in creating these millions of clusters, there's a lot of things that can happen, right? Most of the time, the vast majority of the time in creating millions of clusters, nothing bad happens, which is really great. But even when creating or when it's up, occasionally things don't go as expected. And sometimes this is a downstream dependency. Sometimes this could be an AWS EKS code bug. But also it could be specific to Kubernetes. So I kind of want to dive into some of the interesting Kubernetes learnings because I think those are really helpful just in general. So one of the more interesting ones to me is this semi-recent bug that we got a bug request from a customer. It's basically Kube API server fails to connect to a new webhook pod. So the request basically stated customers running a mutating admission webhook, which I'll show kind of what that means in a minute if you're not familiar with that. It happened to be, in this case, Istio. The EC2 node that the pod for this webhook was running on gets terminated. There's no fin in the TCP stream. A new webhook pod comes up on a new instance to answer requests, but the API server, the EKS managed API server, doesn't connect to this new webhook for almost 15 minutes. So if you're familiar with Istio at all, that this customer is running, when you don't mutate pods, they don't get the Envoy sidecar, which means they can't connect to your services, which is production outage. So that's a bad thing, right? So as we kind of unpacking what does this mean, on sort of a network level, so when we create these Kube API servers, again, with like controller manager, scheduler, a couple other components that we put on there, like we run CloudWatch log agent. So when you actually enable cluster logging on your account, that's CloudWatch log agent, putting your logs into CloudWatch logs. One of the other things that we do when we create these instances is we have a secondary Elastic Network Interface, or ENI, attached to it. Normally, when you have an EC2 instance, you see there's a network interface attached. You can attach secondary interfaces. Well, we attach one, but we attach it in your account. It's a cross-account ENI. This is what enables kubectl exec and logs. So when I want to do a port forward or a logs or exec to get down into my cluster, because I don't, with Kubernetes, that's one of the beautiful things. For debugging, you don't have to use SSH everywhere to get into your pods. How does that work? Well, you, the client, talk to the API server. The API server reaches out over this network interface into you, the customer's VPC, to talk to kubelet, to exec, logs, do whatever it needs to. So this sort of same communication path is what API server uses to talk to webhooks, mutating admission controller webhooks in your cluster. So the API server is reaching out into the customer's account like normal to this webhook pod. As it was getting pod create requests, would talk to this webhook, say, okay, is everything good? Okay, pass it on, you mutate it, the pod gets created. Except in this case, the node, like we said, went away for whatever reason. And the problem was that this TCP connection, TCP stream, or this connection was never remade to the new webhook pod because the Kubernetes scheduler placed it on the right, a new one on on a different node in the correct place. But again, 15 minutes after 15 minutes, finally the API server started connecting to the new one. So what did we do? One of the first things we looked at was, okay, go into the API server, run netstat. What's actually, where's this connection going? And we'd see this foreign address. So the local address is the Kube API server. The foreign address would be the dead node's IP, but it still shows as established. That's weird, right? Like, why is that still there? After we did a bit of digging around, looked into sort of the Linux kernel system tuning parameters, there's this TCP retries 2. I won't read all this text, but the long and short of this means, based on an unacknowledged TCP connection, well, I'll back up a little bit. Go in the Kube API server is using, obviously, TCP here, but it's also using HTTP 2. So the Go net HTTP library is using an HTTP 2 stack to talk to the mutating webhook, which is the server. And when that fin is never sent, the TCP connection is held open up to 15 retries here, which comes to that 15-minute mark. So it was, in effect, there was no fin being sent, but Go's HTTP 2 stack had a bug that forced that connection to not be open. Basically, the client was not sending a ping to say, server, are you still around? And so it just kept the connection open. So there's actually been an upstream Go bug report and patch made for this. That's not quite yet merged. So one of the short-term fix that we actually recommended to this customer in this case is on your Envoy webhook proxy, disable HTTP 2. So have just an HTTP 1 connection. Okay, yes, you might have a few more TCP connections, but you won't have this 15-minute outage. And then also the upstream Kubernetes, there's an upstream change until the Go patch merges, and then Kubernetes upgrades to the next Go version to force the API server to reach out over HTTP1, even if the webhook server offers HTTP2. One of the other interesting edge cases, I think, is etcd. So we alluded to this earlier about how etcd is a managed service, or part of the managed service for you. You're not actually directly exposed to it, but it's the open source key value data store. It's based on the Raft consensus algorithm. And on a high level, I won't get all into what Raft is, but basically Raft relies on what we call consensus. So more than, or some number of the instances in the cluster, the etcd cluster, agreeing on something. So that's how state is maintained. When you make a change in Kubernetes, it gets propagated down into etcd, and the cluster agrees, yes, this is the state of this object. So in etcd, quorum is means that over 50% of the instances in a cluster agree to something. You want odd numbers for this quorum, not even numbers, because if you have a network partition, you want your cluster to continue to function, or at least part of the cluster to continue to function and to work, right? So in this case, we'll use the example of 5. If there was a direct network partition between the 2 and 3 of these 5 instances, you might see these sort of access patterns disappear. The smaller left side of the cluster would not have quorum, because quorum in etcd is more than half, n minus 2 plus 1. We don't meet that here on the left side. So that, if you try to do reads or writes to those nodes from a Kubernetes API server, it's going to fail. But on the right side, 3 out of the 5 nodes are still talking, so they can still continue operation. So this is actually really awesome for high availability. It helps you avoid split brain scenario. That's kind of the other reason for this. Hardly ever, though, interestingly, I mean, this is very helpful and good. Is there a direct split down the middle? Like sometimes it's one direction can talk, but the other can't, or 3 out of the 5 can talk to each other, but one can only talk to one of the others, and it gets really interesting. But for the simple case, we'll just talk about this. So kind of back to the sort of the 3-node case, because that's what EKS operates today. But for every EKS cluster that you create, or that we create for you, there's 3 nodes. So what happens if one of them goes away? Well, we're still good at quorum, right? Like we're over half. But what if that one that you thought was gone is now actually gone? So if one is still around, and then it comes back, but you created a new one, and now you have 4, your quorum just changed. So in this case, what's quorum? It's half plus 1, so that's 3. So now that we're at 4 nodes, and if we get a network partition, we're not in a good space, right? Like we want to avoid split brain, so none of the nodes can answer requests, reads, or writes. And that's obviously the least ideal scenario. So one of the interesting cases that we've seen with etcd that we experienced sort of early on was around this idea of nodes that you think are gone but aren't. Normally, when you terminate an instance, it happens almost immediately. But on a very single-digit number of times, it can take upwards of, for us, we saw a weird event where it took upwards of 20 minutes. And we just so happened to have have a 20-minute timeout in our etcd. We have an etcd nanny manager code. So we terminated this instance thinking it's gone. Our nanny code, what it does is watches for that member to delete, and then once it's actually deleted, removes it from the membership of the cluster. So if you delete an instance but don't go to the etcd API and say, hey, that guy's gone now, the cluster still thinks he's around somewhere because it doesn't know any better. And so in this case, this is what happened. Is we said, okay, we have now a new instance that came online because that one got terminated. But because that member, and eventually that member did actually terminate, but because of our timeouts, and we never actually just cleaned him up, what happens next? Well, we do our normal, say, you do a cluster upgrade, and so we also upgrade your etcd for you. It happens behind the covers, but we our automation thinking, okay, we have 3 nodes, we're good. If we terminate one to do our normal cluster upgrade, everything's going to be fine, right? We're at quorum, we think, but that node was actually never terminated. So this case looks almost the exact same to etcd as 2 and 2, because now 2 instances don't have quorum out of 4. That was, to me, that was like one of those cases where it was a really interesting learning of etcd and kind of how it operates. So for us, some of the lessons that are learned from this are like keep backups of etcd. For this, we already actually had this. So when you create an EKS cluster, we manage the etcd backups for you. Like it's transparent. You don't even know it's happening. So if there were something, sort of a code bug or data corruption or whatever to happen that we couldn't recover from, we have like very regular backups for your etcd cluster. Also monitor your quorum size and membership. So when you think that you have 3 members, make sure, like if you're managing etcd yourself, if you look up how many instances you have and you think, oh, I only have 3 instances in EC2, check etcd, make sure they actually have 3 instances in your cluster. And then check your dependencies are telling the truth. And if they're not, don't assume that they'll get ready in time. Like actually do the manual step of cleaning up. One of the other learnings, this was a fun one too, that we had, and I want to share this one because I think this one is interesting for anyone who's sort of developing on Kubernetes. You don't have to be operating Kubernetes for this case. So IAM for service accounts. It's a feature we recently launched. It's using Kubernetes projected service account volumes and projected token volumes. It's a way that you can, it's a feature we recently launched that lets pods get AWS identities. So if you want a pod to assume an AWS role, to access DynamoDB or S3 or something else like that, this is the feature for that. And you can have different roles for different pods, even on the same node. You don't have to have all of your pods use the same AWS role or user if you're using actual key pairs. So the way this, I won't get into the entire feature, but the way that you as a user of Kubernetes consume this, there's a little bit of setup involved, but you annotate your service account. You put an annotation that's got this EKS Amazon AWS role ARN, and you put your role ARN as the value that you want pods that are using this service account to assume. This is sort of a convenience for you. So when you do this, we have a little bit of magic in the backend. The magic is, again, mutating admission webhook. No surprise, right? So when you submit a pod that uses that service account that you've annotated, we have a webhook that ingests your pod, and then, based on that annotation, we'll update the pod spec. So we'll add sort of all the Kubernetes config that you could add yourself and wouldn't need the annotation in this webhook for, but again, it's a convenience thing. So you can see sort of the line there, and everything below the line gets added by the webhook. Everything above the line is what you define. And if you define existing volumes and environment variables, that would all work. This gets appended at the end. So what's the data path here? Well, it looks very similar to that first bug that we talked about. When I, as a user, go to create a pod, in the base case, I expect it to just go and create, right? Like, it happens normally pretty fast. And if you have an EC2 instance ready and it's got available CPU and memory or other resources that are on your pod spec, like that happens pretty fast. So just for measurements that we took on this, the base case of creating, say, 5,000 pods across 500 nodes. P100, so timed till every one of those 500 pods was actually created, around ballpark 5 minutes, 14 seconds. So that's actually, that's pretty good. Like if you're actually doing a 0 to that rollout, that's pretty fast. As we added this webhook, before we launched, again, this wasn't a fortunately not a customer impacting event. But before we launched this, as we tried this out, those same numbers, 500 nodes, 5,000 pods, as you, the user, create that in the API server, what was happening is the API server reaches out to this webhook hosted on the control plane. The webhook was actually calling back to describe, to say, okay, hey, I see the service account on the pod. Does that service account have the annotation or not? And then getting that response back from the API server, and then responding to the API server's request and saying, hey, here's your mutated pod, or no, it doesn't have there's no annotation, here's just the pod, keep it going. Because of all this back and forth, it seems like, oh, it's just a service account, right? Like you're looking up just a string on a service account. That shouldn't be that long. To create all those, 5,000 pods, the P99 was actually 46 minutes, or P100. So that's like, 900, almost 1,000% worse, right? Like that's unacceptable. You wouldn't want even if your pods weren't using this webhook at all, like that was still the case. It was that slow. And also the other worst part of this was only just over half of the pods were actually getting correctly mutated that needed to be. So when you're writing a controller, you want it to not be slow, right? So what was our fix for this? Well, we actually ended up adding a cache. So in our webhook, as it starts up, it had this, it basically requested what are all the service accounts in the cluster, and then keeping a map just in memory because it's just strings of service accounts to annotations, and then keeping an open watch for updates, deletions, all that kinds of stuff. So we could just update our local cache whenever that happens. So now whenever you as a user go to create a pod or the replica set or data set controller or whatever creates your pod, it's just a single back and forth, and it creates your pod. And so after adding this cache back to the webhook, our P90 or P100 is back down to slightly, maybe 1 second more. It's almost indistinguishable for that same set of number of nodes and pods. So kind of the lessons learned here when you're writing, interacting with Kubernetes, especially when you're writing some sort of mutating or validating admission webhook, keep webhooks as stateless as possible. And when you can't do that, you need some other data to reason about, do I make changes to this webhook or not? It's typically a good idea to add a cache. If you use OPA, Open Policy Agent, it does this. It doesn't actually request from the API server for every resource that you're putting policy on. It actually has its own sort of sidecar cache to check, hey, what's the state of this object or this other object that I need a reference. And then also one of the things is that was another lesson learned was always be measuring your changes. These things are sort of subtle, and if you're not paying attention, especially if you're not operating on large scales and you're like, oh, it just works on this small, 3 nodes, 3 pods or whatever, you might not even notice the difference, but keep measurements of what you're doing. I actually think we're out of time for questions. But I want to say thank you all for coming. I work with a lot of awesome people who make EKS awesome and make it happen. And I'll be available around at the end for questions. But
I think we could take 2 or 3 questions.
2 or 3?
Yeah.
All right.
What runtime platform do you use to run EKS? Is it CRI-O, is it Containerd, is it Docker?
For the customer data plane? Yeah, so in our Amazon managed EKS AMI, or AMI, however you like to say it, we use presently Docker.
Docker?
Yep.
One more?
Hi. Is there something you can say about how you manage PKI for the master in the control plane?
Yeah, so we actually do a separate, we use kubeatom Kube80.
I'm sure about it. Like, if you have a separate system that manages like PKI and distribute certificates, or
No, I mean, yeah, we use EKS Atom for generating and maintaining the certs. So your cluster has an individual like certificate authority that's unique to it, that's self-signed and everything. It's a lot easier to rotate things around that way. Yep. Great.
thank you.
All right, thanks everybody.